So I'm going to take the equation in the form y prime plus ky equals k times qe of t. And the input that I'm interested in is when this is a simple one that you used on the visual that you got 2 points of worth, 2 points worth of work for handing in today, cosine omega t. So if you like k here, so the QE is cosine omega t. That was the physical input. And omega, as you know, is, you have to be careful when you use the word frequency. I assume you got this from a physics class last semester. But anyway, just to remind you, there's a whole yoga of 5 or 6 terms that go whenever you're talking about trigonometric functions. Instead of giving a long explanation, the end of the second page of the notes just gives you a reference list of what you're expected to know for 1803 and physics as well, with a brief 1 or 2 line description of what each of those means. So think of it as something to look up, refer back to if you've forgotten. But omega is what's called the angular frequency or the circular frequency. It's somewhat misleading to call it the frequency, although I probably will. It's the angular frequency. In other words, it's the number of complete oscillations. This cosine omega t is going up and down, right? So a complete oscillation is it goes down and then returns to where it started. That's a complete oscillation. This is only half an oscillation because you didn't give it a chance to get back. Okay, so the number of complete oscillations in how much time? Well, in 2 pi, in the distance 2 pi on the t-axis, in the interval of length 2 pi. Because, for example, if omega is 1, cosine t takes 2 pi to repeat itself, right? If omega were 2, it would repeat itself. It would make 2 complete oscillations in the interval 2 pi. So it's what happens in the interval 2 pi, not what happens in the time interval 1, which is the natural meaning of the word frequency. There's always this factor of 2 pi that floats around to make all your formulas and solutions incorrect. Okay, now, so what I'm out to do is, the problem is, for the physical input, QE, cosine omega t, find the response. In other words, solve the differential equation. In short, for the visual that you looked at, I think I've forgotten the colors now. The input was in green, maybe, but I do remember that the response is in yellow. I think I remember that. So find the response, yellow. And the input was, what color was it, green? Blue, blue. Light blue. Okay, so we got to solve the we got to solve the differential equation. Now, it's a question of how I'm going to solve the differential equation. I'm going to use complex numbers throughout. A, because that's the way it's usually done. B, to give you practice using complex numbers. And I don't think I need any other reasons. So I'm going to use complex numbers. I'm going to complexify. To use complex numbers, what you do is complexification of the problem. So I'm going to complexify the problem. Turn it into the domain of complex numbers. So take the differential equation, turn it into a differential equation involving complex numbers, solve that, and then go back to the real domain to get the answer. Now, why should one do that? Why should one do that? In other words, I didn't give you the real answer. The real answer, why one would do it, is because it's easier. And what makes it easier is the fact that exponentials are very easy to integrate. There's hardly anything easier to integrate than an exponential, where they're polynomials, but unfortunately polynomials occur distressingly little in real life. So complexify the problem. So the notes don't say this, that's why I realized after writing them that I probably, since it's easiest to integrate exponentials, since it's easier to integrate exponentials. And therefore, try to change the trigonometric functions into complex exponentials simply because the work will be easier to do. All right, so let's do it. To change this differential equation, remember I've got cosine omega t here. I'm going to use the fact that e to the I omega t, Euler's formula, that the real part of it is cosine omega t. So I'm going to view this as the real part of this complex function, but I'll throw in the imaginary part too, since at one point we'll need it. Now, what is the equation then that it's going to turn into? Sorry. The complexified equation is going to be y prime plus ky equals, and now instead of the right-hand side k times cosine omega t, I'll use the whole complex exponential. ei omega t. Now, I have a problem because y here in this equation, y means the real function which solves that problem. I therefore cannot continue to call this y because I want y to be a real function. I have to change its name. Since this is a complex function on the right-hand side, I'll have to expect a complex solution to the differential equation. I'm going to call that complex solution y tilde. Now, if I call then that's what I would also use as the designation for the variable. So y tilde is the complex solution, and it's going to have the form y1 plus I times y2. It's going to be the complex solution. And now what I say is, so solve it, find this complex solution. So the program is to find y tilde. That's the complex solution. And then I say all you have to do is take the real part of that, and that will answer the original problem. Then y1, that's the real part of it, right? It's a function. You know, like this is cosine plus sine. Oh, as it was over here, it'll naturally be something different. It'll be something different, but that part of it, the real part, will solve the original problem. The original real ODE.